Whoa. Come on. Should be, how many are there? 2 or 3? 2. There's an extra one. There's 3? There's 3. Okay. In case everybody here shows up. All right. Good morning, everybody. So I went ahead and put together, these are actually old reviews, so I just brought them in, put them into one document. It just gives you some idea because we have 2 weeks left of class. After this week, we have 4 more class meetings, then we have our final. So I wanted to give you kind of as much time to start thinking about the final and just kind of the types of problems that I've asked on finals in the past. So the first, it says here at the top, final exam review, spring 23, part 1. So problems 1 through 20, that's your part 1 of the review. And then the second, if you flip over, it's handwritten. That's another review for a different class. And that one is, I'm calling part 2. And on that one, you can see I actually break it up by sections. So you can actually see what sections those problems are coming from. And it continues to the second page there, right? Or third page of the review. Right, so that's just, so you have it. You can start maybe looking through those and then, ask questions. Do not anticipate that I'm going to give you all the answers to these, hand out, here are all the solutions. So if you have questions, come to me, get help, all right? And this is also not the totality of everything. You need to study, right? Study everything, but here's a starting point, right? Here's something for you to reference. Okay, that's first order of business. Second order of business. Anybody know what these things are? Let me see. Y'all seen these before in any of your other classes? No? Okay, so I don't know how they determine this, but they select classes to do a survey in, and we got selected, right? Both my classes, my Cal 1 and 2, got selected. Now, I'm not happy about this. They say it takes 40 minutes to do this thing, and we don't have time to waste on, it's not a waste, it's valuable information. But at the same time, it's gonna eat up into our class. So what my plan is on this is that I'm gonna make this worth it to you, and I'm gonna offer this as a replacement quiz grade. So you do this, you get a free 100, right? The catch is that I'm not gonna start it till about 20 minutes left in class. So you might have to stay a little bit longer and rush through it, especially if you have a class right after this. Rush through, get it done. Yeah, that sound fair? Okay, so please stop me at about 10, what do we want to do? 20 minutes, so 10:15. All right, somebody flag me down. I'll try and remember, but 10:15 we're gonna have to stop class and do this, yes? All right, fun stuff. All right, we are going to talk about, well, where were we last time? I was trying to convince you that graphing by hand, right, is not that great, but we have the tools to do it, and I gave you some problems from homework, to not graph, but to actually just do the first parts where you're figuring out concave, up and down, and then concave up and down. Any questions on those? I'm happy to do one. to start class? No? Y'all are okay? Have y'all conceded? Or y'all are just like, forget. Yeah? It's the final stretch here, last 2 weeks. All right, well, in that case, I'm moving on. Nobody has questions, we're moving on. So in terms of what you would need to know, like for the final, if you look at the review I just gave you, problem number 16 on that first page, part 1, number 16 is where I ask where a function is increasing, decreasing, local max, local mins, concave up, concave down, inflection points. And notice that the function I gave you there is pretty nice, isn't it? It's a polynomial. However, let's see, on the second one, oh yeah, the second part 2 review, number 12, right? Number 12, increase, decrease, max, min, concave up, concave down, inflection. And then you see where I say sketch? You can just forget that because I didn't ask you to sketch anything. So, but again, that's a polynomial function, so not that bad. So on the final, what I'm looking for is that you understand how to do the method. I'm not trying to bog you down with the algebra and give you a really hard function, right? All right, so we move on. So we are moving on to optimization. And to get this going, I have a question for you. Let's say that I had, I don't know, let's say I wanted to build a fence around like for my dog to run around in, right? In the backyard. I want to build a little fence, a little enclosure for my dog. Let's say I have 100 feet of fence. And what I want to do is I want to make some shape out of this. And let's make it simple. Let's not make it have any curves. Let's make it like a rectangle, okay? So I want to make a rectangle out of this fence, out of that material. So that means that if you go all the way around, right, that should be 100 feet. With me? My question is to you is, you know, I have different ways I could design this, right? I have different ways. Let me get to my question in a second. Can somebody give me one way I could do it? Like, give me the dimensions.
A 10 by 10?
I need to use all 100 feet. So if I do 10 by 10, it's only using 10, 20, 30, 40 feet of fence. Yeah. You're thinking area.
Yeah.
You're thinking area.
30 by 20.
30 by 20, so if I do 30 here, 20 here, then that should add up to be 100 feet of fence. Agreed? I've used all the fence and I've made an enclosure. Can somebody give me a different way of doing it? 35 and 15. What's another way? 40, 10. All of these have the same, I guess, property that if you go around them, the perimeter is 100, yes? How about this? Could I do like a square? Could I do 25, 25? Wouldn't that work? Right, 25 all the way around, that would be 100. All of these are different, right? They look different, they're different shapes, but they all use the 100 feet of fence. Do they all give you the same area? No, right? These are all different areas. I mean, you can see it. 30 times 20 is what? What's the area in there? Oh, geez. What's the area? What? 30 times 20?
600.
600, thank you. 600 square feet is the area, right? What about this? What? 40, 10. Oh, 40, 10. Yeah, thank you, thank you. 40, 10. 400, right? Square feet. So my question was going to be, do we get the same area? But I think we've answered that question, yes? We don't get the same area, do we? This one gives you more area than this one, but they both use the same amount of fence, right? So the question is, how should I make this so that my dog has the most amount of space to run around in? Right? Because I could make it in all these different ways. Like, how about this? Could I do this? (49 by 1), 49 feet long, 1 foot wide, right? So that's 50 feet, then another 50 feet. That's using all the fence, isn't it? What's the area of this one? 49 square feet, right? Huge difference between the area of this and the area of this, isn't there? Huge difference. Plus, that's, I mean, my poor dog, right? Just like, can't even turn around, right? So, optimization is the next section. It has to do with how do you figure out how to get the most out of something, right? Optimize something. And so in this problem, what I would be saying is, look, I've got 100 feet of fence. How do I design this enclosure to maximize the area, to get the maximum area, right? That makes sense? Yeah? So maximizing things is something we've learned to do in this class, right? We can find maxes and mins, and that's the whole point of all of that, was to be able to do word problems where we actually use this somewhere in the real world, right? And it's peaks and valleys. We're trying to find peaks or valleys depending on the problem. This problem we want the highest point. In some problems we want the lowest. Do you remember the one with the fiber optic I showed y'all, you know, going from across the river? And I showed you that we would want to minimize the cost. That was an optimization problem, all right? So how do we do this, right? I mean, obviously this is better than this, and this is better than this. And I never did that to see what that is, and never did that. So rather than checking all the infinite number of possibilities, maybe there's a way we can do this with the calculus. Understand? All right, let's do it. Let's get into this with, let me get to the notes, and then once we get to the notes, I'm gonna come right back to this problem. We're gonna do it, all right? This is where what we say, the rubber meets the road, right? This is where the calculus gets applied to the real world. Now, the problems we do aren't going to seem very real world, but you can imagine that it could extend out into the real world. All right, so make this a little bigger. So once again, we've reached a point where we're going to apply what we've learned to some real problems. There are no like steps. This is like the related rates that y'all love so much, where I gave you that worksheet and you like filled in the boxes, but I said there's no like, not every problem is the same. You have to decipher the information. Same story here, all right? There's basic steps. There's basic steps, but every problem is unique, right? We want to read and understand what the problem is saying, right? Read it, understand what they want you to do. Draw pictures. We've done this before. We want to draw pictures to get an idea of what's happening. We want to introduce any notation, all right? If we need to call something X, call it X. If we need to call something Y, call it Y, whatever. Introduce notation. And then, this is the big one, we want to determine the variable to be optimized. We want to determine what it is that we're trying to optimize. So in the problem with the dog enclosure, we were trying to optimize the what? The area, right? We wanted the most area possible, right? So we want to determine that, what that variable is. That is, and then once we do that, we're going to try and find this thing called an objective function. Objective meaning that's the objective of the entire problem is to try and figure out the maximum of that thing. So we will call that an objective function. Then we want to express the variable to be optimized in terms of the other variables. So we want to express the area in terms of the other variables in the problem. And then we use any given restrictions to express the variable to be optimized in terms of one single other variable. So this is a little hard to explain until you see us do an example. But like in the problem with the dog enclosure, we're trying to figure out the maximum area, right? We need to make sure that we can write the area as a function of a single variable. We need that area to depend on one thing only, because everything we've studied in this class right? The max min, we had functions of one variable, like f of x equals blah, right? Whatever it is, and then we find the max and min. We don't have multiple variables in there, right? We don't have like, we've never dealt with any functions that had more than a single variable in it, right? There is a way to do it, all right? There's a way to find maxes and mins, functions of higher variables. That's Cal 3, all right? That's what you do in Cal 3. Here, we're just stay with a function of one variable. So we're going to do that, and then we're going to use the methods of this section to find the max or min, depending on what we're trying to do, right? So that means you have to distinguish between what approach you're going to use. Pay special attention. This is the part students mess up. Well, along with other stuff, but this is a big one that they mess up. Pay special attention to whether or not the function that you finally wind up with is defined on an open interval or a closed interval. Because we have different methods for finding maxes and mins depending on whether or not we're on a closed interval or an open interval. We started this chapter working on closed intervals, and we had a method for that. And then we went to open intervals, and that's what we've been doing the last few days. So that's going to be an important determination for us, is which of those scenarios we're in. Okay, let's just do the problem. All right, I'm going to do that dog enclosure problem. All right, so here's the way the problem would appear, all right, like in a test or something. You wish to build a rectangular enclosure as shown below. So I'm going to draw a picture. You have 100 feet of fence. Find the dimensions which maximize the area. There you go. That's the way a problem would appear to you. Something like that. So first step, we got to read it and understand it. You understand it? I mean, we kind of talked about it already. So everyone got it? I need to draw my picture, sorry. Here's the picture I would give you. That's what I want, okay? I want you to find the dimensions of this rectangle that are going to maximize the area, but you have 100 feet of fence, right? Let's go. Let's do the solution. So here's my solution. First thing I'm going to do is I'm going to write down, I already have a picture, so I'm going to write down the thing it is that I'm trying to optimize, which in this case is what? The area. Okay. So I'm going to write down area, right? Area is what I'm trying to optimize. I'm going to call it capital A, right? Now, what is area? Well, what is the area of that? Length times width, right? But I don't have anything labeled, do I? So let's label this, and I'm not going to use L and W. I could L and W, but I'm just going to use X here and Y here. So see, I have assigned those variables to the problem, right? I've assigned those. So by assigning X and Y there, I know now the area can be determined, right? You can tell me what area is, but somebody has to provide you X and Y, don't they? X and Y. And right now, I do not have the area in terms of a single variable. I have two variables, right? I need to get it to one variable. So this right here is going to be my objective. Okay, my objective is to try and find the maximum of this. But I have what we call a constraint. The constraint is that this can't be any dimensions I want, right? Like I can't make X 300 and make Y 500. I can't, right? I have a constraint. What is my constraint? 100. So what has to be 100? Well, X, can X be 100?
2x.
the perimeter has to be 100, right? The perimeter has to be 100. So how do I express the perimeter of this in terms of x and y? So let me write this down. The perimeter here must be 100. But the perimeter of this rectangle is the distance around it, right? So like if you were to start here and go around, you'd have x plus y plus x plus y. So how many x's is that? 2 x's. So what I can say here is that 2x plus 2y, right? That's the perimeter, must be 100, right? This is a constraint. I mean, yes, the area is x times y, but x and y can't be whatever I want. They have to satisfy that equation. Y'all got it? Now, what I'm going to do is, again, trying to get this in terms of a single variable, right? I'm going to come over here, and I'm going to use this equation and solve it for either x or y, my choice. Take that answer and plug that answer in for x or y here, and then we will have area in terms of a single variable. Okay, so let me come over here. I'm going to solve for y. So to solve for y, I subtract 2x on both sides, and then I divide both sides by 2. Right? Divide by 2 on everything, and I get an expression for y, don't I? I have y in terms of x. And now what I'm going to do is I'm going to take this 50 minus x, that's what y is, and I'm going to plug it in up there. So area here, again, can't just be anything. It has to be x times the y, but the y is 50 minus x. And now, do you agree that the area is now a function of a single variable? All you have to do now is give me x, and then I can tell you the area, right? I'm going to go another step. I'm going to change my notation slightly. I'm going to write it like this, and then we'll discuss why. So all I did there was distributed x through, right? That's all I did. But what did I do on the left side? Instead of writing area, I wrote a with the parenthesis x. That's because I want you to see, we're looking at it kind of like a function of x now, right? Like initially the area relied on 2 things, but the fact that it now relies on 1 thing, I can say the area is a function of x. And that leads us into what we've been doing, right? How do we find the maximum of a function of a single variable? Well, we use the stuff we've been doing, right? Y'all okay?
Where do you get the x?
What x?
Oh, okay,
This?
oh, okay, you for the left.
No, this, okay, over here I distributed. Yeah, I distributed the x through there. Here I'm just rewriting, this is just notation that lets everybody know, hey, now I'm aware of the fact that the area depends on 1 thing. Okay, we drew pictures, we labeled variables, we figured out what our objective was, we figured out a constraint, we used that constraint to come back and rewrite our objective as a function of a single variable, right? The next critical step is the one I just said people mess up. You have to decide now, are you going to go down the road of trying to find the max of this using the closed interval method or the open interval method? So that means we need to talk about the domain of this. And when you look at this initially, you'd say, oh, that's a polynomial, right? And the domain is everything. But we're within the framework of the geometric problem here, right? We only have so much fence to work with here. So is there any restriction that you can give me physically on x? Like what's the smallest x could be? What's the smallest value of x I could have here?
As long as it's greater than 0.
Greater than 0? How about 0 itself? Could x be 0? It seems like no, right? Because then you won't have an enclosure, will you? But that would be possible. It would be like you make this width here 0, and then the rest of the fence is for these sides, right? But then you don't have an enclosure. But that's like the absolute extreme of what I could have. And it would be, like if I was hiring someone to do that, and they said, yeah, we're going to make it 0 wide, we'd fire them, right? It doesn't make any sense, but it's an extreme number. We can't have a negative x, right? But we could have 0, even though it's stupid to have 0, yes? So that would be the absolute smallest. What would be the biggest? Be careful. What would be the biggest value of x? 50, not 100, okay? 50, because you have two sides, right? This side here is x and this is y. So if I said, okay, the biggest x could be would be 100, then you would need 200 feet of fence to start this. But if I say 50, I could put 50 here, but then what would y be? 0, which again is the other stupid extreme, you see? But so do you see it has to be between 0 and 50? It could be 0, even though it doesn't make any sense, and it could be 50, which wouldn't make sense, but it could also be anything in between, yes? So I'm going to do this. I'm going to find the max of this on the closed interval 0, 50. I want to know the biggest this can be on that closed interval. Do you all have questions? What's the closed interval method? What do you do? Find the derivative. Okay, let's find the derivative. So I'm using the closed interval method. Look at this is 4.1. 4.1 is the section that we covered this in. So we take the derivative, a prime x. That derivative is 50 minus 2x, right? What do we do with the derivative? Find out when it's 0, find out when it doesn't exist. Okay, so find the critical numbers, the critical points. So when is this derivative 0? And when does the derivative not exist? So when is that derivative 0? Set it equal to 0. Let's see, add 2x to both sides, divide by 2. You get x is 25. That's one critical number, potentially. Does this derivative ever not exist? No, it's a linear function. It's no problems here. So that's it. So I only have one critical number. Does it live in here? Does 25 live in there? Yeah, so we keep it, right? Questions? All right, drum roll. What next? You're not done. You cannot tell me right now that 25 is going to give you the maximum. You have to show me, you have to prove it to me. What? Okay, so we're going to take that number 25, and we're going to take the two endpoints, and we're going to plug those into the original function. That's the closed interval method. We're not doing a number line, dotted, partition test points. That's the open interval method, right? So we're doing closed interval. So now what I do is I take the two endpoints and I plug them into the original function. Here's the original function right here. I'm going to take the first endpoint, plug in 0 into that. I'm going to plug in 50, and I'm going to plug in 25. The biggest number I get out is the maximum, for sure. The smallest number I get out is the minimum. So let's plug 0 in here. 0 in here, right here. It's 0, isn't it? We already knew that. If we made one side of it 0, the area's got to be 0. And the formula confirms that. Plug 0 in here, you get 0. How about 50? What do you get if you plug in 50? 50 times 50 is 50 squared minus 50 squared, which is 0 again, right? So you get 0. Now, 25 times 25. What's 25? 50 times 25 minus 25 squared. 625. 625. This is our max area. That's the maximum area. Have I answered the question? No. What did the question ask? Find the dimensions. Find the dimensions, right? That maximize this thing. So this is the maximum area I'm going to get, but the dimensions are this. Well, I need x to be 25 feet, right? 25 feet. By the way, this area is square feet. Just if you want units on here, that's square feet. X is 25. What would y be then? Well, one thing you could do, I mean, you might just be able to look at this. We already said 25 by 25, right, would work. But go back to where our constraint was. I erased it. Do you remember our constraint? We solved for y. Do you remember we solved for y back on constraint? We had this right here. Remember that? Wait, was it that? Minus just x. Okay, we had divided by 2. That's right. Yeah, it was this, right? We had solved for y. Okay, well, if x is 25, put 25 in here, what's y? 25 as well. That's our answer. You're going to make a square, right? That's what that's telling you. We're making a square. What do y'all think? If we have 100 feet of fence and we want to make a rectangle that has the most area, then we're going to make a square, and it's going to have an area of 625 feet. It'll be 25 by 25. This okay? All right, I'm going to change the problem now. All right? Change the problem. Same situation. Okay? I'm going to erase the word rectangle. You wish to build an enclosure as shown below. You have 100 feet of fence still. Right? I'm no longer requiring this to be a rectangle. What I'm requiring is that it looks like what I'm about to put up here. I have 3 dogs. Okay? I don't have 3 dogs, but let's say I had 3 dogs and I want to separate them. I want to give them each the equal area, all right? So, but when you look at this picture, I'm telling you that the area of this, this, and this, they're all the same, right? So the dimensions of this and this and this need to be equal. All right? Give me the dimensions of this so I get the maximum area. All right, so let's write down the objective. What's the objective? What are we trying to maximize? Area still. Okay. What is the area? Well, I don't have anything labeled, do I? So we have some choices here of how we do this. I could call this x right here if I wanted to. And then wouldn't that be x? And then that would be x as well, right? So let's call this x. And then the whole thing, all the way from here to here, would be 3x, right? And then this height right here is the same for all of these pieces, isn't it? And so that, let's call that y. Y is going to be this side, right? That goes from here to here. So what is the area? What is the area of that entire enclosure then? 3x times y, right? It's this times this. So 3xy.